let's get started. 307. All right, welcome back. Started the recording, right? Yeah. Okay. All right, here we are. Still in week 4. Okay, so hopefully you've gotten started on reading chapter 12 about collections, right? It's about lists and sets. So we've seen lists already, and of course the sets here are not the set theory sets, but they're a data structure that doesn't include duplicates. So there are no duplicates in the set, and there's no guaranteed order of the elements. Okay, so we might get to talking about those today, maybe not. Definitely on Friday. And then what's the other chapter on recursive data? So again, it's kind of about lists as well, because they're an example of recursive data, a recursive data structure. And I don't recall. It really only talks about lists in here, but definitely you'll want to read this as well. All right. So, one of the things I should mention, I suppose, is that there are a number of things in this course that are like confusing for students in the beginning, and like for example, constructors. We have these things called constructors. If we go back to the list type, here they have an example of something kind of like the list type for num list, and it's got these things called constructors, NL-empty and NL-link. And I guess I should have said this before, but just to avoid confusion, that these really have almost nothing to do with the things called constructors in C++ or Java. Okay, and so it's probably, you'll have an easier time if you just kind of, when you walk in this room and when you're doing the homework for this class, it's like you're entering a portal into an alternate universe, okay, where everything is wrong, basically. not exactly, but we're in functional programming land where things are different. So constructors are like almost entirely different. I mean, they're similar in the sense that they help you to construct, values of some type, but that's pretty much the only similarity. Okay. So I think what we'll do today is actually, last time at the end I kind of rushed some stuff because we ran out of time, and so I guess I kind of want to go back a little bit and clarify some things, and probably what I'll do is we'll cover a little bit more set theory again. Okay, so we looked at a few things, a few set theory concepts like the union and intersection. Okay, and we talked about cardinality of sets, and then we also had these other operations called the Cartesian product and the disjoint union. Okay, so but then I mentioned this thing where to show that two sets have the same cardinality, then what you do is you show a bijective mapping between them. So, and I kind of skipped over that because I assume that you've seen it before, but we could, I think it might be useful for us to go into a little more detail on, what exactly does that mean? What's a bijection? Let's remind ourselves what that means. And so, it really boils down to two concepts. One, an injective mapping, where by mapping I mean function. Mapping is something that maps elements from one set into another. It's a function from one set to another. So you can have an injective mapping and a surjective mapping. Okay, so let's look at what those mean. Okay, so suppose we have two sets, call them A and B. Okay, two sets. Then F, a function or a mapping from A to B, is injective. Okay, if so first I'll just draw a picture. All right, let's draw a picture to get some intuition for what it means. Okay, so suppose A looks something like this, and it has some elements, right? A could be infinite, who knows? Okay, and then B maybe looks something like this. It also has elements. Okay, and then F sends every element of A to some element of B. So we'll say that F is injective if for every element of A, it maps to a unique element of B. Something like this. Okay, and then there could be more elements of B that F doesn't map anything to. But the point is that every single element of A, every distinct element, has a distinct element of B that it maps to. And so what this is, it's sort of we call it injective because you're like injecting all of A into B. You're sort of embedding it inside of B in a way that doesn't lose any information. Okay, so you're not taking 2 points and collapsing them down into one, but all of A is kind of preserved within B. So it's sort of like saying that B is like at least as big as A. Okay? So it's sort of like A is less than or equal to B, if you want to think of it that way. If there exists an injective mapping from A to B, or an injection. All right? So we could write this using logic in a few different ways. So one way to say that F is injective, kind of the standard way, would be to say that, well, for any 2 points, or any 2 elements, x and y in A, what is it? F of x equals f of y implies x equals y. Okay, so that's one way to say that F is injective. And you can read that basically if you have 2 elements from A and they're equal on the other side after doing the mapping, then they must have been equal to begin with. Because we know an injective mapping does not collapse elements. So if x and y are collapsed, then it really x and y must have just been the same element. That's what this is saying. So there's an equivalent way of writing it. It might be intuitively a little bit easier to grasp. Just say, okay, for all x and y in A, if x is not equal to y, right, then f of x is not equal to f of y. Okay? So again, if you have 2 elements that are not the same in A, then they will not be the same in B when mapped by x. Okay, and so these 2 things are, logically equivalent statements, at least, in sort of everyday mathematics. These are the same. Okay, but there's another way of saying the same thing that is kind of better for us. Okay, so I'll show you what that is. It's going to be this. There exists a g, which is a function in the reverse direction, such that for all x in A, that you can do this. That if you send x over to B with f, and then send it back with g, you get back to where you started. So if you do this, it's equal to x. Okay? So this is kind of, it's another way of saying that f is injective. If there exists a function like this, there's a way to get back. So again, appealing to our intuition of what it means to be injective, it means that it's sort of faithfully embedded inside B, which means that in principle there should be some way to recover everything, right? And so this is where we're saying, okay, there is a function to come back, to recover A. So that the round trip, if you do f and then g, you get right back where you started for any element in A. Okay, so we like this one. We like this one because we like functions. And this kind of is more, it's just a little bit stronger, I guess, because it kind of, in a way, this kind of tells you, if you have a function, then it tells you how to recover it. Gives you more information. All right. So that's what it means for a function to be injective. Okay? And so now we can look at the other direction, the other important property for functions, which is surjective. F from A to B is surjective. Okay, if we can draw another picture. This time I'll draw A a little bit bigger, just to kind of illustrate. Okay, so this time we require that every element of B is mapped to by F from something. So for every element of B, there's some element in A that gets mapped to that element in B by F. Okay, so if that's an element of B, okay, every one of these is covered. Maybe I drew too many. It's kind of annoying. Okay, but then, it could be the case that there are even more elements in A that get mapped to kind of the same points. Okay, it's A doesn't have to be injective. It could be collapsing elements. All right, that's what F is doing. Okay, so this is sort of where injective meant. Injective you can interpret as meaning sort of, A is like smaller than or equal to B, or like less than or equal to B in a way. Well, this is the other way around, where if there's a surjective mapping from A to B, then it sort of is like B is less than or equal to A. Okay, and so we can write this logically as well. I'll say, let's see how we want to do this. Let's say for all y in B, need a consistent style for B. There exists an x in A such that f of x is equal to y. Okay, so for every element in B, there exists some x in A such that f of x goes to that y. Okay? Right, but now, again, there's an alternate formulation of this that we like a little bit more, okay? And I'll write it like this. Like there just exists a G, again, in the opposite direction, such that for all y in B, okay, so now if we're going to start with an element of B, what can we do with it? Well, we can send it over to A with G, and then send it back with F. So that's what we're going to do. Okay, so you can do G of Y, and then send that through F, and this should be equal to Y. Okay, so this is kind of doing the other round trip, starting from B. If you do the round trip this way, you get back to where you started. All right. So we like this one as well. All right, and so now we can get to this idea of a bijection. Okay, so we'll say F is bijective if and only if, F is injective and surjective. All right, and so what we can do, sort of, is like combine these two things. And although, in general, these G's don't have to be the same, but to make things easier, if you can make it the same, so let's suppose there's just one G, such that both of these properties hold with respect to F and G. And so this is kind of what I want to work with, is we'll say, okay, one, it suffices to show, or how do I want to word this? I'll say, okay, two sets are equivalent if there exists a bijective mapping between them, right? So to show two sets are equivalent, to show A and B are equivalent, it suffices to show that there exists a pair of functions, f going from A to B, and g going in the opposite direction, such that for all elements in A, the round trip is the identity, right? The round trip gets you back to where you started, and the same for all elements of B, but like that. Okay. So if you want to show that two sets are equivalent, you can do this. Show that there's a pair of functions that are each other's inverse. That these two things hold. And so you can think of these functions as being like conversion functions. Okay, the f converts an A into a B, and g converts a B back into an A. And it's like a lossless conversion that you can always get back. You can recover the information from doing the conversion. And you can do it in either direction. So the sets are equivalent. So this is the like kind of the notion of equivalence that I'm going to lift to types. Okay, so it's just like this, but we're going to say, well, two types are equivalent if you can come up with two functions such that this holds. Okay, we'll say that two types are equivalent if they're like interconvertible. You can convert between them. Okay, so that's kind of what I want to use. That's our notion of equivalence for types that we're going to use. Okay. So what that means, like if I were to give you two types and ask you if they're equivalent, well, if the answer is yes, then I could ask you to show me why they're equivalent, and what you would do is give me two functions. Give me two functions, then maybe argue, why these properties hold, why these two conditions hold. Okay. So what I want to do is show you some examples of doing that. Okay, that's what we'll do today. We'll look at some types and think about sort of counting the number of elements of the types, and then also looking at equivalent types and how to show that they're equivalent. Okay, we'll do it in Pirate. Yeah. Okay. All right, and one of the things that I mentioned at the very end last time, so I didn't have much time, is that I want to have this idea of like finite types, and I'll just use numbers to denote them, because all I really care about is how many elements they have. Okay, so 0 will be a type that has 0 elements. Okay, type with 0 elements. Sort of the empty type. Okay, and sometimes it's called void. And again, that's not the same void that you're familiar with from C or whatever. So, forget about that. Void, it means it's empty. So, there's no such thing as returning void in functional programming world, because in order to return a void, you'd have to produce an element that doesn't exist. All right? Okay, but then, 1 has 1 element. And that's often called unit. Okay, the unit type. And 2, so you should be pretty familiar with 2, because that's Boolean, right? That's the Boolean type. And then, but you could have a finite type with 3 elements and 4 and 5. Okay, all of these things. All right? So I will show you in Pirate now how we can encode these types And then we can look at products and sums as well. All right? So let's go ahead and open up an editor window. Okay? So I'm going to start with, you might think it's really weird to do this, and I suppose it kind of is, but let's do the 0 type. All right? So I'm going to say data 0. I could call it void, but I'll call it 0. Okay? And, well, that's it. There's our 0 type. All right? There are no constructors. Okay, let's see what Pirate does. I called this file types.r, and it type checks. Okay? Pirate will accept this definition. All right? Now, yeah, you might think this is a stupid thing to do. Like, why in the world would you ever have a 0 type? And I suppose I could possibly think of some example. It's a way to encode impossibility into your type system. Okay, where you say, well, I don't know. Maybe there's not really a realistic use case for this in Pirate, but in some other programming languages there are. All right, but there's something interesting you can do though. So let's suppose, if you had a value of type 0, what could you do with it? Again, it's kind of funny, but let's say 0 elim whatever, choose a name, and suppose it takes an element of type 0. And maybe this will be generic over some type, like this. Oops. So this is kind of weird. But I guess I'm just illustrating here that the 0 is kind of a special type here, where it's like, in a way, it's sort of supremely difficult to create a value of type 0, because, well, it's impossible. But then, dual to that is that if you were to have a value of type 0, it's sort of like supremely powerful. Like you can do anything you want with it. Okay, so this is the way. What we're saying here is that, well, for any type, if you give me a 0, then I can give you an element of that type. Because, well, if you give me a 0, I can do anything I want. Okay, maybe I should call this x falso. Okay, because this corresponds to a principle in formal logic called x falso quadlibet or something. Okay, so what would you do here? You do case analysis on 0, and then, well, you have to consider all the cases, and there are none. So there you go. And this will type check and work. Okay, so that's how you can use a value of type 0. You just do this, and Pirate will let you. It'll be like, okay, that's something of type A, because, well, all the cases have type A, because that's the normal type checking rule. Okay. Now we can move on to some more practical examples. Okay. So let's look at 1, the data type for 1. 1. Okay. So for 1, it'll have one constructor, and I'll just call it 1 with lowercase. Okay, that type checks. Now, there's not a whole lot of interesting things you could do with 1, but so the normal use case for a type like this would be, this is sort of like returning void, right? If you think in C++, sometimes you run a function just for its side effect. Maybe it prints something or whatever. You don't really care about its return value. You're just kind of running it so that it does something. So in that case, in a programming language like this, you would return the 1 type. That would be your return type. Because then, the return value then is not really encoding any information. It's just the 1 value. There's only one of them. Okay, so it's pretty uninteresting. Okay, so now let's look at 2. And I don't know what to call the constructors, but I could call them like O and I. Okay, just to have 2 different names. Oops. Okay, so now we have a finite type with 2 elements. All right, let's see if this type checks. It does. Okay, so now this is the first one that's a little more interesting because, well, we already have a type like this that's built into Pirate, right? We have a type that has two elements, two values, and it's the Boolean type. Okay, so what we'd say is that this is equivalent to the Boolean type. It's it's not equal. Pirate doesn't consider them to be the same. It won't let you pass in a 2 where it expects a Boolean, because it'll say that 2 and Boolean are not the same. But they are equivalent, which means that they're interconvertible. Okay, and so we can witness that fact that they're equivalent by giving the conversion functions. So we can do that. Okay, so let's say we want to convert a 2 into a bool. Say 2 to bool, and it'll take a value of type 2 and produce a Boolean result. Okay, check that that makes sense so far. Okay, type checks. Now what will we do? Well, if we've got a 2, then we'll do what we always do and use cases. And well, we have to handle each case. And you could decide here, what should 0 correspond to, and what should O and what should I correspond to. But we could send O to false and I to true. That would be one way. Okay. And now we need a function going in the other direction. Bool to 2, Boolean, produce 2. And in this one, how do you use a Boolean? Well, you use a conditional if else. Say if B, then whatever we choose, it should match this. So if B is true, then we want to go to I. Else O. Okay. And so now that we have these defined, from 2 to bool and bool to 2, then it should be the case that for any, let's say for any value of type 2, then if you send it to bool and then send it back, you should get back the original value. And we should have the other direction as well for all B of type Boolean. If you do bool to 2 and then send it back, you should get back the original. And so, if these types were infinite, then we wouldn't be able to check all the possibilities. But because we're dealing with some finite types here, you could actually we could verify these conditions by just enumerating all the possibilities. Okay, so we can do that here in a check block. I could say, okay, well, let's do the 2 values. There's only 2 possibilities here. So one of them was O. We can try that, and well, the test passed. So we can try it with I as well. And that one passed. And so there we've actually verified this condition because, we've actually checked all the values of type 2. There's only 2 of them. And then we can do the same for bools. False, true, and it should work. Oops. Okay. Yeah, now that works too. So we verified both properties. I was about to say something and I forget what it was. Oh yeah, right. So, okay. Now this wasn't the only choice for our conversion functions. We could have done something else as well, right? We could have swapped them. could have said that O goes to true and I goes to false. And then as long as we swap here as well, then we could do the same proof. And it would work. Okay, so these bijections are not necessarily unique. Okay, there's actually two possibilities here. Yeah. Okay. So that's all I want to do with finite types, but you could do this with more than two as well. You could go up to 3 or 4 and have some types with like different names for the constructors and things, and show that they're equivalent. All right, but now I want to move on to products and sums. Okay, so this is where maybe what I'll do is revisit what I started getting at last time, which was that using this notion of equivalence that we have on types, then there are some interesting identities that hold. Okay, there are some equivalences that hold. Okay, things like 0 plus A for any type A is equivalent to A. Okay, where we know what 0 is. It's the empty type. And so this holds for any A. Okay, and likewise for this. Okay, and so what this means is that these things are interconvertible. That we could come up with functions to do the conversions. Okay, but there are a whole lot of interesting equivalences that hold. We have this. Okay, we have so what do these mean? This is commutativity of sums. This is associativity of sum. Okay, what else is there? There's probably, how I can remind myself. Let me just look. There's a certain kind of, we're looking at algebraic structures here. Let's see. Whoops. Go away. Too big. Right, there's associative, and okay. Now we've covered sums. Okay. So this is a common thing in math and like abstract algebra, because what we're really looking at with these types, with the equivalence relation, is a certain algebraic structure. But so we're not going to get into that, of course. But I just want to show you some examples here of interesting equivalences. All right. Here it is. Okay. So we also have a 1 element, and so maybe predictably we're going to have things like this with respect to our product operation. Product types. Okay. And of course, the product is also associative. Okay, and this is where it's common for the product to not be commutative, but for us it is. Okay, so maybe you could think of like an example of a product that's not commutative would be like matrix multiplication. Okay, so it's fairly common for these kinds of algebraic structures for the product to not be commutative, but for us it is. There's an equivalence here, because if you have the type of pairs A and B is going to be equivalent to the type of pairs B and A by the conversion function that just swaps the elements. And it's actually the same. Swap will take you in both directions. So you only need one function. So we'll do that in Pirate in a second. Okay, but I just want to show you, because there's a whole bunch of these that hold. Okay, and so it's very cool. I think it's really cool that you can do this. Okay, so we also have the distributivity like this. Okay, so if you have a type that is it's like a pair with an A on the left and on the right, it's either a B or a C, then that's going to be equivalent to C, this. So now it's either one of these or one of these, where this is a pair of A and B and this is a pair of A and C. And if you think this through, then you can kind of convince yourself why that's the case. And as an exercise, you can program the conversion between these, but you have to have the types. So I'll show you how you can do that, because Pirate has products and sums, so we can easily encode our product and our sum that we're looking at here in Pirate. All right, and of course you can do this the other way too, where A is like on the other side, and you distribute from the right. That will also work. Okay. So let's look at some of these. Okay. So let's see how we can encode products. And I'll do it with this pair type. I'll just call it pair. It'll be the type of pairs of A and B. So this is like the product of A and B. Okay. It'll have one constructor that I'll call pair, and maybe A of type A and B of type B. Right? So it just holds a pair. Okay? So, like I said, Pirate's data type mechanism kind of builds in products and sums. And so we can easily take like the simplest possible example of just the product type. Okay? And we can make it like this. Okay? And then we have some of these identities that we looked at, okay, with respect to the product. And so we could actually sort of prove these if we wanted to. So let's look at this one. All right, let's make a function that converts an A cross B into a B cross A. Oops. Okay, and I'll call it swap. Sorry if it's, move it up a little bit. Okay, I'll call it swap. Okay, so it's generic in these two types A and B, and it'll take a pair of AB and produce a pair BA. See if that makes sense. Okay, so at least so far it's good. Now what do we do? Cases, pair, same thing as always. Okay, there's one possibility. Now what do we do? Yep. Yeah, because so what it wants us to put here is something of this type, pair BA. And what's value of that type look like? Well, it's going to have to use this constructor, and on the left it has to be one of these, which for us was this. So it came from the right of the other pair. All right. So there we go. We just swapped the elements. All right. And that's it. So now this is our conversion that witnesses that equivalence of the commutativity of products. Now to really prove it, we can't do like we did before, because we have no way of enumerating all possible values of A and B, because we don't even know what A and B are. This is a totally generic instruction. Yeah?
So that wouldn't be considered recursion, right? Because you've already defined the function above it?
Right.
Okay.
This is not recursive because, well, the name swap of the function doesn't appear anywhere in the body. So it doesn't refer to itself. It's just kind of pulling out. It just does case analysis on the pair and then builds a new pair. So it's a pretty straightforward computation. Okay? Right, and so you could prove this. You could prove that, like, but you'd have to do it sort of, it wouldn't be too hard. I don't know if I kind of want to move on to other stuff. But you could prove that, you know, swap of a pair gives you back the original pair. Okay? Now, right, okay, so I'll show you the sum type. Oops. Before we run out of time. And I'll call it either. Okay? So it'll look kind of similar. But this one is supposed to be, you know, either an A or a B. So I'll just pick some names for the constructors. We'll say left. Left will have an A, or, you know, right has a B. See if that type checks. It does. Okay, so Pirate's okay with this definition. And now we can do something, you know, kind of similar. Say we want to do the equivalent, because I think, right, the sum is also supposed to be commutative. So we should be able to do a swap on the sums as well. Right? So let's try that. And I'll call this co-swap. Never mind the name. You know, I'd say the hardest part of programming is choosing names for things. So, all right, so this will take something of type either. Oh, I have to have the variables, type variables. Okay. It'll take an either of A and B and produce either of BA. Oops. Check that. Okay, so far so good. Now, anyone have an idea of how to do this? Cases? Okay. Yeah, let's do cases on the value that we have, or the, you know, the expression here. Then what goes in the cases?
Left and right.
Okay. Yeah, there will be a case for left where you have an A in there. Then what do you do?
Return right.
Yeah. And we'll do the same thing here. I think that's right. There you go. Okay, so, you know, you just, whenever it was a left of A, then, well, if you've got an A here and you want to turn it into an either a BA, then it needs to go on the right. So that's what we do. And then a right of B goes to a left of B. Okay, that's easy enough. All right. So yeah, you could, like, you know, for fun, you could yourself do something like this. Okay, where this is a pair with A on the left and with either BC on the right. Okay, and you could define functions to go from here to here, in that direction, and back, and try to convince yourself that they really are inverse operations. Okay. And now, you know, we still got a little bit of time. And so this whole thing actually goes further. And I mentioned last time, not only do we have products and sums, but we also have these things called exponentials. But I don't know if I can get to those quite yet, because they become especially relevant when we get to higher order functions, because basically we haven't really got to talking about functions yet. And so exponentials are functions. But there's also this kind of algebraic interpretation of functions that is really neat and kind of carries this analogy even further. So I don't know if we can get to that yet, but I guess I'll just start talking about functions a little bit. Okay, well, we have a few minutes. All right, and so, you know, the basic idea is that we have an arrow type. that just like you could take products of two types and you can take the sum of two types, well, you can do this as well. Okay, this is a type. It's the type of functions from A to B. Okay, and we're generally going to stick to this, where there's only one argument type. All right, and well, if you want to have more than one argument, what can you do? You could put a product there. You could have something like this. All right, and so now here's a function. It's the type of functions with two arguments, essentially. But there's only one type here because the product type is one type. So we can do everything we want with just this arrow type for functions. All right, and so there's an alternate notation for this type that looks like this. Okay, b raised to the a. So that's why it's an exponential. So that's why these are called exponentials. So we have product sums and exponentials. And so one of the things that we've been concerned with products and sums is sort of counting the number of elements in a type. And how did you do it with products? Well, you would just you take the product. So, right, at least in the very least in the finite case, when our types are finite, then the number of elements in a product type is equal to the product of the number of elements in the two types. Okay, and for sums, it was very similar. Okay, and so you may not be surprised at this point to see the following. That the number of elements of an exponential is just the number of elements in B, which is the sort of like a return type, raised to the power of the number of elements of A. All right. These are true when the types are finite. All right. Okay, and then you may also be able to imagine that there are a bunch of these algebraic identities that hold for this type as well, and there's one of them that is especially important that I want to get to eventually. But so we'll probably kind of drop this stuff for now. So on Friday we'll start talking about the actual reading. But then when we get to higher order functions, I want to pick this back up a little bit to get back to exponentials, because that's really kind of the essence of functions. Okay? So we have a few minutes left. So yeah.
Can you switch back to your pirate?
Sure. Okay. I'll commit this code. I'll commit it to the in-class directory in the repository. Okay, so now there's only one thing left, and we have to see if there's a quiz today. Okay. All right. See you Friday.